right, we're going to go ahead and get started. So thank you everyone for joining us. My name is Cynthia Jenks. I'm the Associate Laboratory Director for Physical Sciences. We want to welcome everyone to our very first virtual Eugene P. Wigner lecture featuring Nobel Laureate in Physics, Dr. Samuel Ting. A little bit about the lecture series to start. The laboratory launched the Wigner Distinguished Lecture Series in Science, Technology, and Policy on November 4th, 2013, the 70th anniversary of the first criticality at the graphite reactor. The goals of this lecture series are to invigorate scientific discovery, spur technological innovation, and initiate productive scientific policy debate among, obviously, the participants in this lecture series and those of us here at Oak Ridge National Laboratory, as well as our distinguished guests as well. The lecture series honors Eugene Wigner. He was a chemical engineer by training, and as we like to say, a physicist by inclination, a founder of the field of nuclear engineering, a role model for coupling basic and applied work that has continued to transcend what we do here at Oak Ridge National Laboratory today. Wigner himself was the winner of the Nobel Prize in Physics in 1963. Based on work he did in the 60s, he published a paper on the unreasonable effectiveness of mathematics in the natural sciences. Our speaker's background in physics aligns perfectly with Wigner's paper, as mathematics is the workhorse of all sciences aimed at understanding the physical world as we know it. By way of introduction to Dr. Samuel Ting, he is the Thomas Dudley Professor of Physics at the Massachusetts Institute of Technology. He has led international collaborations in experimental physics on board the US Space Shuttle Discovery and the International Space Station, shown here. He was awarded the Nobel Prize in Physics in 1976 for his discovery of the J particle, which is a subatomic particle consisting of a charm quark and a charm antiquark. Dr. Ting attended the University of Michigan and studied engineering, mathematics, and physics. In 1959, he was awarded a BSc in mathematics and physics. And in 1962, he earned a doctorate in physics. As you might imagine, in addition to his Nobel Prize, he has won many awards, including, but not limited to, one important, of course, to us through the Department of Energy, but the Ernest Orlando Lawrence Award, NASA's Public Service Medal, the Ricci Prize for Peace from the World Federation of Scientists, the Gold Medal for Science from Italy, the Gordon Plate Award of the American Academy of Achievement, the Golden Leopard Award for Excellence from Italy. And today, his lecture is going to be titled, The Latest Results from Alpha Magnetic Spectrometer Experiment on the International Space Station. Now, before Dr. Ting gets started, a little bit of housekeeping. If you have questions, which we hope you do for Dr. Ting, please post them in the chat rather than raise your hand. Again, post them in chat rather than raising your hand. And we will take some time at the end of the session to answer as many questions as possible, ending, of course, by 5:15. And with that, it is my absolute pleasure to introduce Dr. Samuel Ting. Thank you very much for joining us.
Thank you. It's a great honor for me to give the Eugene P. Wigner lecture. I first heard of his name when I was a graduate student at University of Michigan. And also I had studied nuclear engineering, and there was this classical book on neutron chain reactor by Wigner and Weinberg. I later on know him and his brother-in-law, Paul Dirac. He really is a truly good physicist. What I would like to do today is to share with you the latest results on the Alpha Magnetic Spectrometer experiment on the International Space Station, otherwise known as ISS. I've always been involved in large international collaborations. I started my career in the electron synchrotron in Hamburg, measuring the size of electron, and then come back to the United States. I broke heaven for the discovery of the J particle. I worked for many years in Hamburg again for the work on gluons, and then spent more than 20 years at the Large Electron-Positron Collider testing standard model. And after that, I went to work on space shuttle and space station. Our group has always received strong support from Europe and Asia. In recent years, for the work on the space shuttle and space station, most of the financial support come from outside the United States. My first international collaboration is in the 70s with the 30 billion electron volt electron-positron collider in Hamburg, known as the Mark J experiment. And that's where I met Marcel de Marteau, whom I just saw again a minute ago. Now it's at Oak Ridge. And an important work was on positron-electron collision, produce quark, antiquark. On the left side, you see it forms two jets. If there's a gluon come out, which then you see three jets, and the size of the jet which increase with gluon energy. And if you put the three jets apart, and you see the jet energy distribution agrees with quantum chromodynamics require a quark. Three jets can come from also quark-quark fragmentation energy difference. So see a three jet doesn't mean anything, but it's a statistical agreement with QCD confirm the existence of gluons. The second international collaboration is the L3 experiment at CERN with 100 GeV electron, 100 GeV positron collision. And this is a large international collaboration involving 20 countries, United States, Soviet Union, China, Taiwan, and Europe. And this experiment has a magnet weight 10,000 tons come from Soviet Union. And also had a 300-ton uranium calorimeter made by ETAP. I think Yuri Kameshkov, I don't know if he's here or not, from University of Tennessee, and that's him in his younger days, made a tremendous contribution to this experiment. We also developed BGO crystal with Ken Reed, which is now also at Oak Ridge. In 83, when we first started the experiment, the world's total production of BGO was 4 kilograms per year. We need 12 tons. And so one of the technical development was the production of 12-ton BGO crystal in 3 years. And I think Ken Reed, if my memory is right, you were at Princeton at that time. And BGO crystal now is commonly used in industry and in medicine. In the L3 experiment, we have 300 papers and 300 PhD degree was awarded. But the result can be summarized in a few sentences. Namely, there are 3 kinds of electrons, the electron, mu, and tau. There are only 6 kinds of quarks, U, D, S, C, B, and T, with the existing energy range. To me, the most important thing is the electrons and quarks have no size. Their radius is less than 10 to the minus 13 centimeter. When I first started doing the experiments, the size of the electron I said was at 10 to the minus 14 centimeter. After 30 years, we managed to reduce the radius by 3 orders of magnitude, but never seem to be able to find the radius. All our results are in excellent agreement with the current theory of elementary particles. This is rather unfortunate, because when an experiment agrees with theory, what you learn is limited. It's when the experiment confronts the theory, you learn something new. The fourth international collaboration is the MS experiment on the International Space Station. And this is a picture of the MS experiment. The International Space Station has a dimension of 109 meters by 80 meters. It weighs 420 tons. It rotates around the Earth every 93 minutes. The construction cost is about 10 to the 11 dollars. Why AMS on the space station? Charged cosmic rays have mass. Therefore, they are absorbed by 100 kilometers of Earth's atmosphere, which is about the size of 10 meters of water. So property of charged cosmic ray cannot be studied on the ground. On the ground, you can measure the total energy. To study the charge and momentum require a magnetic spectrometer in space. When I started, somebody showed me this cartoon, and so at this time we face reality. We are not exactly rocket scientists, because before this experiment, myself, the MIT group, none of my collaborators have any experience in space, on space work. Also in space, experiments are costly, and this is another cartoon which said that we have just decided to launch money directly into space was cheaper. The most important contribution from the United States Department of Energy is to accept my advice to organize a blue ribbon panel review of AMS by distinguished scientists, Nobel laureates, member of National Academy of Science, and experienced astronauts. And so the committee reviews us every 3 to 5 years. And there's Barry Barish, George Smoot, and Nobel laureates, and also Jim Cronin and Saul Perlmutter. And the next review is September this year. It is because of this quality of this review, we always receive large international support. So the detector was constructed in Europe and Asia, assembled and tested at CERN, and European Space Agency, under NASA supervision. It is a space version of a precision detector used in accelerators. On top is a transition radiation detector identifying electron and positrons. 9 layers of silicon tracker measure charge and momentum. A brain image Cherenkov counter measure charge and energy. An electromagnetic calorimeter measure energy of electron positron. 2 blanks of simulation counter, time of flight counter, measure Z and energy. A magnet measure the sign of the charge and momentum. Anti-coincidence incidence counter reject cosmic ray coming from the side. So there are 5 independent systems provide independent information of cosmic rays. So there's a TRD, time of flight tracker plus magnet, ring image Cherenkov counter equals. So electron will leave this trace, proton leave this trace, positron leave this trace, antiproton leave this, antihelium leave this trace. And so we measure the momentum in GeV. Rigidity is a term, means momentum per unit charge. Charge is the location on the periodic table. Energy is GeV over A. A is the atomic number. And then also measure charge Z, measure the flux. The flux is a unit of number of events per second per stir radian per square meter per GeV. And so we systematically measure all the elementary particles and measure elements across the periodic table. First is a magnet. Before us, there's nobody put a magnetic spectrometer in space. And the reason is very simple, because at lower Earth orbit, you still have magnetic field. And so if you're not careful, a magnet, one end will point to the north, another end point to the source, to the south. And so your space shuttle and space station would be lose control. And that's why it was difficult to put a magnet in space. So to build a magnet, we actually built 10 magnets using permanent magnet material. The reason the Chinese were involved is the best permanent magnet material come from Inner Mongolia, which is part of China. 7 magnets to ensure the magnet has no torque, has no field leakage, and can be constructed with iron. So we have 4,000 pieces of permanent magnet material, arrange the magnetic field with 2 closed loops. And with its 2 closed loops, looking from Earth's magnetic field, this and this will cancel each other, this and this will cancel each other, this and this will cancel each other. So no field leak outside. No field leak outside means you don't need the ion. Also, the astronaut can go near the magnet. So we built 3 full magnets, one to do acceleration and vibration to simulate the condition rocket leave the ground. Another is to do a destructive test. The magnet is made out of 4,000 pieces. And if during the shuttle lift the ground, if one piece comes out, it will not be very good. And third is the flight magnet. Silicon Tracker is a large international collaboration. There are a total of 9 silicon trackers, measure the coordinate between 5 to 10 microns, measure momentum, and with energy loss, measure charge. We did extensive calibration at CERN before we sent to space. And so we located AMS at a 400 GeV proton beam and measure with the protons, electrons, positons, pions, simulate high energy protons. And this is the measurement. The blue is the test data, and the yellow is the Monte Carlo. This shows the difference agrees with each other to about 5 order of magnitude. It means we understand the detector and understand the accuracy of the measurement. So it was sent to space about 10 years ago, May 16, 2011, and with 6 astronauts. In space, the data is transmitted to a Tetra satellite, to White Sands, to Marshall Space Flight Center, then to the Payload Operation Control Center located at CERN. 2 months before launch to space, I suddenly realized this connection, even though guaranteed by NASA, but perhaps would be a good idea, we put in a reserve system. And so we installed a computer and trained the astronaut to learn how to use this computer. This is just a simple computer. On the ground, the price is unit 10 to the 3. Once you want to put in space, you have to add 3 zeros behind in the cost. This is the first event, a proton of 7 billion electron volt, and this is the front view, this is the side view, and this is TRD, time of flight, silicon tracker, and the ring image Cherenkov counter, and ECOM. And this is 10 years later, is 178 billion cosmic rays. This is a helium event with energy 35.6 billion electron volt. In space, you cannot see the detector. Therefore, you have to constantly assume, all the time assume something will go wrong. And therefore, you have to check them. If you know something goes wrong, you can correct it. If something goes wrong, you do not know, you're going to make a mistake. And so we continuously calibrate the detector with protons by comparing the upper part of the spectrometer measurement with the lower part of the spectrometer measurement. And this shows the blue one is the proton spectrometer from the upper part minus the lower part, and compare with the Monte Carlo simulation. Again, to fourth order magnitude, they agree with each other. There are no plans for another magnetic spectrometer in space. It took us nearly 20 years to build this, and therefore all results are analyzed by multiple international teams. The reason we do that is when you want the accuracy of 1%, the judgment, what is signal, what is background, always come in. So this is the measurement of proton from 1 billion electron volt to 2,000 billion electron volt. And compare with the average, this measurement by the French, by the Spanish, by MIT, by the Taiwanese. When they agree within 1%, we'll publish the data. Let me first talk about light antimatter, positons, and antiprotons in the cosmos. There are three sources of positons. The first is if there's a dark matter collide with another dark matter, you produce energy. Energy can decay into positons or antiprotons. So dark matter produce antiprotons and positons. Another is ordinary cosmic rays, such as protons and helium, interact with interstellar media, produce positon from collisions. Another source is the new astrophysics sources, such as pulsar, which will produce positon from pulsars. So positon have three sources, three known sources. Before AMS, this is the 50 years record of all the measurement of positons and electrons. Positon is in this axis, electron in this axis. Let me mention, because the positon spectrum, cosmic ray spectrum decrease sharply with energy. For display purpose, the spectrum is always defined as the flux multiplied by energy to the third power, so you can see it better. And there has no physics meaning except for display purpose. With this graph, you can tolerate many theories. Indeed, there are many theories to explain the spectrum of major positon and electrons. This is our measurement today of positons and electrons. And you can see this is the electron from very low energy, few hundred MeV, to trillion electron volt. This positron flux is lower than electron. So you multiply by 10 to see the difference. You can see right away positron and electron are totally different. What is the origin? Where is the origin of cosmic electrons? The first thing you notice is the contribution from cosmic ray collision is this part, which is very small. And this is total 28.1 million electrons from very low energy to multi-trillion electron volt. the electron flux can be described by two power law functions, A and B, namely phi E minus equal to constant Ca times e to the gamma A plus constant Cb e gamma B. So there are four parameters can accurately describe the 28 million electrons. And so this is the measurement, and the contribution from collision is very small. And this is power law A, power law B. You feed the data to this, you see power law A plus power law B, the green curve, are in perfect agreement with the data. The question is, what is the origin of power law A and power law B? No one so far has been able to provide an explanation. And there's a question, what is the origin of positons? Positons are quite different. The low energy positons mostly come from cosmic ray collision. Indeed, a model calculation fits to our data. And then the question is, what is the rest of the positon at high energy? What is this axis? The axis cannot be from cosmic ray collision, so it must have been from pulsars or dark matter, because those are the only three sources we know. So the positon spectrum is the sum of a low energy part from cosmic collision and from high energy from pulsar or dark matter. Analytically, it can be fit with two power law plus a cutoff. Electron can be fit with two power law, but positron cannot be fit with two power law without a cutoff of energy ES, because the spectrum goes down. The cutoff is established at an energy about 1 trillion electron volt and with a confidence level more than 4 sigma. The first question you ask, could positron come from pulsars? Pulsar is a rotating neutron star, has a strong magnetic field, and therefore when a light ray goes into the magnetic field, it produces electron positron. So high energy positron can come from pulsars. Pulsars do not produce antiprotons because the photon does not produce a p bar p because the mass of protons is so high. So the latest result shows the antiproton have exactly a similar twin of positron. This is the antiproton spectrum, and this is the positron spectrum. And the ratio of antiproton to positron is exactly 2.0 plus minus 0.35, and is independent of energy. But remember, antiproton cannot come from pulsar. Therefore, most likely, positron is not from pulsar. Most of the universe is not visible, and it's called dark matter. Galaxies seen by the telescope is on the left, we're familiar with. And galaxy, if you could see, dark matter can be imagined as from the right. There are many, many models to predict dark matter production of positons. So this is a model with a mass of 1.2 TeV, including, of course, low energy positron from cosmic ray collision. So this is the theory. This is our measurement. The measurement up to now is in good agreement with the theory. What we need now is to reduce the systematic error. This dropout is very important, and this comes from the fact a finite energy dark matter collision cannot produce infinite energy positrons. Basically, conservation of energy and momentum require the spectrum to go down. So by the lifetime of Space Station 2028, if the trend continues, we should see this point. This point above 1000 GeV. And this point will come from cosmic ray collision. So the speed fast drop down cannot be explained by pulsars or any other method. So to summarize, electrons originate from different sources than positons. The electron spectrum comes from two power laws. Nobody knows what is the origin of the two power laws. The positron flux is the sum of the low energy part from cosmic ray collision plus a high energy part with a cutoff energy from pulsars or from dark matter. But antiproton spectrum rule out the pulsar origin of positons. Now I would like to share with you some surprising results from precision measurement of cosmic nuclei. We have 5 detectors measured periodic element in periodic table. So this is the correlation between the time of flight counter and the silicon tracker. And this is the measured spectrum from hydrogen, helium, lithium, all the way to iron, cobalt, and nickel. We have published the results in blue. The reason is they have reached the total events of more than 1 million. And the one in white is yet to be published, and when we have about 1 million events. We want to make a 1% measurement. Before us, historically, people always assume there are 2 classes of cosmic rays. Primary cosmic ray, proton, helium, carbon, oxygen, silicon, ion, are produced during the lifetime of stars and accelerated by supernova. They propagate through the interstellar medium before they reach the Earth. So imagine what happened. I lost.
Yeah, I see that. Maybe
Yeah.
just go back to PowerPoint on the bottom. The orange one. Yep, that one.
Yes.
There.
Measurement of primary cosmic ray flux are fundamental to the understanding of the origin, acceleration, propagation process of cosmic ray in galaxies. Before us, there are many measurements. I list all of them on the right. To measure the light primary cosmic ray of helium, carbon, oxygen from balloons and satellites. And the yellow and blue is helium, green is carbon, red is oxygen from low kinetic energy to 1000 GeV. With such a large error, you accommodate many theories. When you measure it accurately, this is the MS result. Very surprisingly, above 60 GeV rigidity, the primary cosmic ray have identical rigidity dependence. Their absolute value is different, but the functional behavior as functional rigidity is exactly the same. It's one form up to 200 GeV and another form above 200 GeV to 2 TeV. And this is 125 million helium, 14 million carbon, and 12 million oxygen. Nobody predicts that. Nobody thought it would behave like this. Before AMS, there are also heavier primary cosmic ray, neon, magnesium, and silicon, and there are many measurements listed on the left, and you put them together, they look like this. What we found, heavier element, neon, magnesium, silicon, have their own identical rigidity behavior, but they are different from helium, carbon, oxygen. And so primary cosmic ray have at least 2 classes. In each class, the rigidity dependence is the same. And this is not predicted, not imagined, or not mentioned in any theory. So the American Physical Society once a while announce AMS results, and this is our press announcement. And let me just, it's a long article, let me just quote an interesting one said, we can now turn stars into high energy lab, which the universe is running for us. This is a statement made by Peter Biermann of Max Planck Institute for Radio Astronomy in Germany. The heaviest primary cosmic ray is iron. Iron is a very important element in cosmic ray theory because it is a heavy element produced in stellar evolution. Iron has a large interaction cross-section with the interstellar medium, and therefore it probes the closest distance from the galaxy. Helium has the smallest interaction cross-section, probe the furthest part of the galaxy. Yet, unexpectedly, iron and helium have identical rigidity dependence above 200 GeV. You can see from here onwards, they are the same. So, iron rigidity dependence does not belong to its neighbor neon magnetism silicon, but it belongs to helium, carbon, oxygen. So in primary cosmic ray, there are two classes, but most unexpected is iron doesn't belong to the heavy class, belong to the light class. And so there was another announcement end of last year from APS that with the measurement of iron, the team has reached atomic number frontier, won't be crossed for years to come. Then there's a secondary cosmic ray. Secondary cosmic ray, lithium, beryllium, boron, fluorine, nuclei in cosmic ray are produced by collision of primary cosmic ray with interstellar media, produce secondary cosmic ray. Measurement of secondary cosmic ray nuclear flux are important in the understanding of propagation of cosmic ray in the galaxy. In fact, lithium, beryllium, boron, and fluorine on Earth are produced by cosmic rays. So there are many measurements of light nuclei, lithium, beryllium, boron. These measurements are very, very difficult because the rate is very low. And this is the enormous measurement before AMS. And this one shows the measurement of lithium. The red point is AMS result, and these are the previous result. And this is the Cabot model of cosmic rays. And these three things are not related to each other. And this is from very low energy to very high energy. What we found, the secondary cosmic ray, lithium, beryllium, boron, also have their identical rigidity dependence to high accuracy. But their rigidity dependence is different from the primary cosmic ray. It's really very strange. From 60 GeV to 2000 GeV, their energy dependence are exactly the same. And these are the difference of normalization factor in the total rate. Our latest result on fluorine is Z equal to 9. Fluorine is difficult nuclei to measure above 10 GeV. There are very little measurement. And these are all the measurements today from very low energy to very high energy. We found secondary cosmic fluorine does not belong to lithium, beryllium, boron, and has its own rigidity dependence. So secondary cosmic ray also have two classes above 30 GeV. So primary have two classes, secondary have two classes. The cosmic rays in space from 1 or 2 GeV to 1,000 GeV, they form families. They are not distributed at random. I think in 2 weeks' time, there will be a paper in APS on the third group of cosmic ray. So we have primary cosmic ray, proton, helium, carbon, oxygen. We have secondary cosmic ray. And then we found out there's a third group, nitrogen, sodium, aluminum. They are produced both in stars or in the interstellar medium. So it's partially primary, partially secondary. This is the measurement of sodium and compared with theory and compared with the early measurement. Look at sodium. Red point is our measurement from 6 billion electron volt to 2,000 billion electron volt. And the blue is the sum of secondary component and the primary component. Secondary component is 1.36 times the fluorine flux. Primary is 3.6% times silicon. Aluminum, the secondary components is 104 times fluorine. Primary component is 10% of silicon. Nitrogen, secondary component 62% boron. Primary component 9% oxygen. And when you add up this spectrum, you have a perfect agreement with the data over energy from few GeV to a few thousand GeV, with the indication the primary component gradually increases with energy. Very strange effect. So there's a new group of cosmic ray, nitrogen, sodium, aluminum. So all the cosmic ray we can see, we can observe, have one is primary, which has 2 classes, one is secondary, which has 2 classes, and then we have another class, partially primary, partially secondary. So we will continue precision study of nuclei through the lifetime of space station, explore the rest of the uncharted region. And the reason we have not published this region is we want to wait to have, I mentioned just now, we just wait, we have million events so the accuracy can be in the % level. So we published 20 papers, and most of them are selected as editor suggestion, and some of them are announced by APS. We also looked for quarks. Quarks and electrons and positons are produced at the very beginning of the universe. Search for quarks was the main physics topic in accelerators since the 80s. So we are now performing a more sensitive search for quarks. Quarks have a charge 2/3 and 1/3. This is our charge measurement in 2/3 and 1/3. We have measured 3 billion signals of protons charge 1 and helium charge 2. And there's no charge 2/3. So free quarks are not found. And then let me share with you some surprises in solar physics. Cosmic radiation from Milky Way is 90 radiation man equivalent per year. And lethal dose is about 300 rand. But this is it's very difficult to do experiments, so this probably is not too accurate. And if you go to Mars, going and back will take about 3 years. And if you have no protection, perhaps there's no need to come back. Also, if you want to establish a long-term base on the moon, you certainly will need to know the cosmic ray radiation. This is our measurement of proton flux above 100 MeV and shows mostly in northern hemisphere and also in a region where the magnetic field is very weak. It's known as South Atlantic anomaly. So this is protons. And this is helium. Helium is very distributed very differently from protons. So helium has two isotopes, helium-4 and helium-3. In the energy region between 100 MeV and 4,000 MeV, over a large region around the equator on the magnetic angle plus minus 35 degrees, only helium-3 exists. Helium-4 lives outside. In the equator region, over a large region, there's no helium-3, no helium-4. This is the yearly, monthly, daily proton flux from 10-year result of 5.5 billion proton signals. We observe periodic structure which are momentum dependent, whichever show in a minute. So this is 2011, 2012, 13, 14, 15, 16, 17, 18, and 19. This is 1 GeV, 1.9 GeV, 3 GeV, 4 GeV, all the way to high energies. You can see at low energy, you have repeated structures daily, monthly, yearly. These are new and unique probe of fundamental property of solar physics and provide safe information for interplanetary travel. So they provide a connection to activities on the surface of the sun. Corona holes are regions where plasma density and temperature are low, and so they appear darker in the image. This image is taken by Solar Dynamic Observatory from NASA. And they are sources for high-speed solar wind, which affect the Earth. The rotation of the sun causes multiple periods in the flux. If there's no corona holes, there's no period. If you only have one corona hole, you have a period of 27 days, and that is also known as Bartol's rotation. You have two corona holes separated by 180 degrees, you have 13.5 day period. And you have three corona holes separated by 120, it's 9 day periods. So you should expect to see 27, 13.5, and 9 day period. This indeed is a structure we just measured, periodic structure in the daily proton flux in 2016. The upper is the first half of 2016, and the lower is the second half. You look at function momentum from 1 GeV to 20 GeV, and then 20 to 100. So you open it up. You will see 9 day period, 13.5 day period, 27 day period. In each of these, it changes with energy or with momentum. You can see the 13.5 day increases up to 20 GeV, and then from 20 GeV, it decreases. And here you can see more clearly the 13.5 day, it increases with the rigidity, and then again decreases with rigidity. And similarly for 9 days. And this is the first time people have such accurate data to see this behavior. So we will continue to collect data for the lifetime of the space station. We will try to understand the origin of elementary particles, positrons, electrons, antiprotons, and antideutrons, and so forth. I already said the existence of antiproton spectrum that's exactly the same as positron, same to rule out the pulsar origin of positrons. By 2028, we should be able to see this point, and this will make sure we did see the origin of dark matter. And we will measure the rest of the element and try to understand the origin of cosmic rays. Let me now share with you the question of antimatter. Antimatter was proposed by the brother-in-law of Eugene Wigner, Paul Dirac, who published the paper and shows, I think it was 1928, shows in the theory of relativity and in quantum theory, mass appear as square, and therefore can be minus m times minus m. And Dirac asked, what is minus m? And leads to the theory of antimatter. This is the discovery of antimatter by Carl Anderson, and shows in a cloud chamber of an electron bends in the opposite direction. From accelerators, and notice there's an active participation in the heavy ion work at CERN from Oak Ridge, and we know that every particle has an antiparticle. Every nuclei, deuteron, helium, have antiparticle, anti-deuteron, anti-helium. And this is one of my first independent work, that is the observation of antideutrons. A fundamental question is the existence of antimatter universe. The Big Bang origin of the universe require matter and antimatter to be equally abundant at the very hot beginning. Helium has 2 protons, 2 neutrons, so its charge is +2. Anti-helium have 2 antiprotons, charge -2, and 2 antineutrons. We provide a direct search for antimatter, because anti-helium will bend in one way and the helium will bend in the opposite way. So far, we see 28 million electrons, 7 billion protons, 1.1 billion helium, and tens of millions nuclei. And we have seen 1.9 million positron, 0.6 million antiproton, and we have a few candidates of anti-helium, and we want to know where is anti-carbon, where is anti-oxygen. This is a rather fundamental question. We're not making any announcement yet, mainly because we want to get more events and to see where's anti-carbon. So when AMS was first launched into space, there's an article in Scientific American. In 10 years on the space station, we have recorded more than 175 billion cosmic rays. The accuracy and the characteristics of the data simultaneously for many different types of cosmic ray require the development of a new model for the universe, because none of our results can be explained by the theory. So thank you. So I finish now.
Thank you very much. That was a fantastic talk. Really appreciated hearing about the properties and origins of cosmic rays, potential existence of antimatter, and just the amazing work, as it says, of this crown jewel of the Alpha Magnetic Spectrometer. For attendees, please go ahead and put your questions into the Q&A or the chat. With that, we do actually have one question so far.
Yes.
So Yuming Guo asks, aberration of the magnetic spectrometer gets worse over time. If geometric and chromatic aberration are not corrected on the International Space Station, what would be the impact of the aberration effects, like peak broadening or change in shape of the peaks?
No, we calibrate the detector every 2 minutes.
Okay, so aberration is not an issue.
Yeah. As I mentioned, this is an important question.
Yes, it is.
Because on an accelerator, you can shut down the accelerator and go take a look, make a measurement. And you cannot go to the space station.
Right.
Also, in space, something I didn't realize, there's no such thing as repair, as shutdown, as upgrade.
Mm-hmm.
And there's no weekend, no Christmas. Because
no weekend, no Christmas, right?
Yeah, and because the space station rotating around the Earth every 93 minutes.
Mm-hmm.
And the Earth rotating around the sun. And so there's a great variation of temperature. And also there's arriving and departure of space vehicles to bring food, bring supplies. So you always have to assume something may go wrong. We're always has 4 people on ship to watch all the instrument.
Wow, just for that one instrument.
Yeah, it's not automatic. It's just always 4 people check all the instrument, and we use high energy proton to check the detector, every detector, and compare with each other.
Okay. We have another question. Somebody asked, does the dark matter model fitting the positron data imply a dark matter particle at 1.2 TeV?
Yes, implies that 1.2, the plus minus some number, I don't know, 0.1 or 0.2.
Okay.
Yeah.
Okay.
Let me mention, okay, there are hundreds of models in explaining our data. Not only dark matter, but the spectrum of nuclei and electrons also. All these models fix the parameter and can explain one set of data, but the same parameter cannot explain other set of data. So far, we don't have a theory which can explain what we measure.
Thank you. So somebody else asked, and I actually had the same question as well. You mentioned that there are no more plans for any additional magnetic spectrometers in space. So why is that? Or if you could, so why is that? And if you could, what would you put up?
This detector, NASA, according to NASA accounting, cost $2.5 billion.
Mm-hmm.
Okay. And I think it's not exactly easy to get $25 billion to build an experiment.
Okay.
At least I do not know, I'm somewhat familiar with the plans in Italy, in Europe, in the United States, and in China and Japan. But nobody is proposing a magnetic spectrometer.
Okay, all right. So somebody else asked, is there any meaning to the small structures in the positron spectrum?
Small structure?
Yes, small structures in the positron spectrum.
Let me look. It doesn't move anymore. Why it doesn't move anymore?
It's moving on our end. I'm not sure what slide that is.
Yes, I think I can remember this slide. This is positron spectrum. There's no structures.
Okay.
No significant structure.
No significant structure. Maybe that's a better way to put it. And somebody else asked, Have anti-lithium and anti-beryllium, et cetera, already been detected?
No, no.
Not yet. Okay.
No.
And if
This-
also, oh, go ahead.
Yeah, I mentioned carbon, anti-carbon, anti-oxygen, mainly because the rate is very high for carbon and oxygen.
Okay. So
That's
the reason
only
you're
reason.
looking
Yeah,
at anti-carbon and antioxidants is because the rates are high.
yeah, yeah.
Okay. And let's see, somebody else asked, the periods of proton flux from coronal holes were identical, but why would the proton flux be less than the latter half of the year? Less in the latter half of the year?
But you talk about solar physics.
Yes, I assume so. Oh. Coronal holes.
Why the proton flux? And I do not know how to answer this question.
Okay.
This is the measurement.
Okay.
Yeah. Let me mention, okay, I know nothing about solar physics.
Okay.
And,
Fair enough. Okay. So somebody else asked, okay. Somebody wrote, is the collecting area the only way to improve higher energy fluxes? And would a detector farther away from Earth help?
No, or measurement, and doesn't really change because there's no more atmosphere, and unless you go out of the solar system,
Okay.
there is a satellite, a non-magnetic satellite made by Stone Voyager, called Voyager, and it uses DDX, the size of your hand, that now has after 50 years has left the solar system. They use DDX, measure very low energy protons and deuterons, and their measurement can extrapolate directly to our measurement at high energy.
Thank you. And Yuri asks, how many anti-helium candidates have you seen?
Quite a few.
Quite a few.
Yeah. But we are not making any announcement, mainly because I would like to see anti-carbon, anti-oxygen.
Before. Okay.
Yeah.
Okay. Somebody also asked, you were talking about the cost to put up a new a spectrometer into space. How much funding does it actually take to maintain, I don't know if you know this, the current spectrometer, and who is the predominant source of the funding to maintain that?
There's no, it's a permanent magnet, and so you don't require maintenance.
Okay, but is the people, who's funding the people to the people who are up in space for this experiment?
Let me see. Let me go to the front.
Or maybe I don't know if it's NASA or if it's an international group that's.
Let me just a minute. What happened? How come it doesn't move anymore?
Yeah, that I don't know.
Why does it move?
Oops. Yeah.
There are 15 countries, 60 institutes in this experiment. And there are large support from Germany, from most of the European countries, and also from
okay.
CERN, also from CERN.
Okay.
And DOE maintain a good support of the MIT group.
Okay.
Mm.
Okay. There was a follow-up on the question about the small structures, where you said that we didn't see that that the small structures weren't significant, and they asked about small structures in the electron spectrum. Are there any significance to those?
No.
No.
You know, when you have billions of events, you're going to see 3 or 4 sigma effect. If you don't see that, there's something wrong. Because
Okay.
there's statistical fluctuations.
Of course.
Yeah.
That data. And the last question I have for now, and of course, if anybody else has any questions, please go ahead and put them in. You talked a bit about how you have to, constantly calibrate the detectors. Have there actually been any outages over the lifetime of the spectrometer, and what kinds of outages have they been? Or are they just mostly tied to communications?
We have 9 layers of silicon detector.
Uh-huh.
They have to operate with a constant temperature of 10 degrees C.
10 degrees.
Yeah. And they are cooled by cooling system by circulating CO2 on the electronics. And this, to circulate the CO2, you need pumps. And so we designed the system. It actually was designed by NICAF. Marcel de Marteau must know NICAF, by the Dutch, using phase transition. From liquid to gas, you absorb the heat. And so we bought a pump, and this NASA developed from ours. And to be safe, we only need one, we purchased 12.
12?
Yeah.
Wow.
Put 4 on the space station, so you have a 400% redundancy, 300 or 400%.
Yeah, exactly.
And then you have an identical system on the ground. All the elements have identical system on the ground. And so
really? Okay, that's interesting.
You can check them. And then I think it's February 28th, 2014, suddenly one pump stopped.
Took a while, so that's good.
Yeah. But even though the guarantee for 3 years, indeed, 3 years, it stopped almost on time. One stopped, and then you cannot guarantee the other 3 will not stop.
Right.
So I went to NASA, said we need to change these pumps. And NASA said, no. You designed the experiment without replacement. Everything is sealed.
Oh my goodness.
Yeah, and we cannot do that. And also you have high pressure lines, 30 atmosphere lines coming to the pump, and there are 8 of them. So this cannot be done.
Oh, okay.
So I told them, why don't we think together? And so we work with them. And we also had some people from Holland, the original people who designed the pump. After 6 months, they decided this can be done. Yeah. And then we developed 12 new pumps and sent 4 in. With 2 astronauts do 6-hour spacewalk 4 times.
Wow.
Yeah, and cut the lines and connect it together. This kind of things happen mainly because none of us has worked in space before. The concept of repair just simply didn't come to us.
Right, right.
You realize when it's too late.
Right. And as you said early on with the cartoon, yeah. We're not rocket scientists.
So now everything's working, but you never know what will happen to you the next minute.
Okay. And
well,
maybe
basically, I spend about 4 hours on the Zoom with the control room and talk to the physicists. You really need to watch carefully.
Right.
Yeah.
And we have one, so we have time for one last question. So somebody asked, does the raw data get processed before being sent to Earth? Because you mentioned there's a computer up in the space station, or is the raw data sent back to Earth for processing?
The raw data is 7 gigabit per second. We have 600 microprocessors, specially designed microprocessors, and very, very fast microprocessors, and process them into 2 megabit per second to process down, to come to the ground. From 7 gigabit to 2 megabit, to 10 megabit. So it's do a lot of background subtraction, zero subtraction in space. And we have an identical system on the ground. So every time if you want to change a software, you test on the ground first before it's into space.
Ah, got it. That makes sense. All right, with that, I really want to thank you very much for being here for this Wigner lecture. It's been an absolute pleasure to meet you. I certainly wish we could have done this in person, and I do certainly hope you will be able to come to Oak Ridge sometime soon. Thank you very much. And on behalf of the participants, the attendees, again, thank you for this fantastic lecture.